Welcome back. This is the final module. In this module, we're going to talk about statistics, believe it or not. Here's the important point I want to convey to you. That what really matters is clear thinking about our research. Fancy statistics can help. We can certainly help you with understanding such things. I want to give you a little bit of information about statistics if you want it, but the key idea is to go back to the earlier modules when we're talking about clear thinking, counterfactuals, proper comparisons, confirmation bias, and the importance of reporting what we might call negative results from that silly story of the prisoners in the middle of the desert. This module is about statistical inference, which again I hope just sets some ideas for how we understand our research. You might notice this funny drawing on this main slide. This is a picture of a fascinating device called a quincunx. And what happens here is we drop a ball from the very top center of that device, and it goes down kind of like, I think the game's Plinko, plink, 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 and all of those equally spaced nails, if you will, on a board. And what happens is the balls that fall down will end up making a bell-shaped curve of balls at the very bottom of the device. So by dropping a ball or a set of balls from the very top and letting them plink down, we get a normal bell-shaped curve. A wonderful metaphor for how, if you will, Mother Nature gives bell-shaped curves for so many things, such as height and sometimes weight and IQ and other interesting things we find in Mother Nature. Quincunx. My favorite one of these, by the way, editorially, is in the Boston Science Museum. As a young guy, I used to go there and just sit in front of that quincunx and watch that thing go. That's some really nerdy stuff, maybe why I'm talking to you this afternoon. All right, first a little language. What we have when doing statistics ultimately is some group of people or group of groups that we're going to talk about as the target population. Yeah, I don't like this language either. The term target is not comforting to me, but this is the language of modern statistical analysis, and so we're going to use it for consistency, but maybe someday source population or other terms can be used. So this purplish circle we're going to talk about as the target population. If we could measure everyone in here, everyone's height or health or weight or any other measure we wanted to do, if we could measure all of those people and calculate that average we would call a parameter. A parameter, that's, if you will, the true number of, say, BMI, body mass index, in the target population. And we got that by measuring every single person with perfect precision, and nothing else changed. So were we able to do this, we end up calculating a parameter, and that's often denoted by that capital Y with a bar over it. That's the average of the parameter. We hardly ever get to measure everybody in a population. Instead, we take a sample, and ideally it might be some sort of random sample, but it could be a convenient sample. It could be just sort of intercepting people as they walk down the sidewalk with your clipboard and say, you want to take a survey? Or it could be something vastly more sophisticated. But we take a subset of the target population and we call that a sample. It's a subset of the population. What might be interesting to you is that the calculations from that sample are what we call statistics. The population calculation is called a parameter. The sample is called a statistic. So statistics from the sample aim to typically represent what the whole population would be. Statistics aim to represent the parameter. So we might measure a subset of people, 15, 20, 2,000, from the whole population, and if we do it right and do our calculations right, we can have a good estimate of the whole population. In election season, as you know, places like the Gallup poll can measure, say, 3,000 people in a country of 300 million and get a pretty precise estimate of who's going to win the election. That's pretty astonishing. It's all because of the power of statistics and some related ideas. So we might take one sample out of this target population that hopefully we can define very well. We're going to study school kids in St. Paul, Minnesota, who attended public school in the year 2017, so on and so forth, very well defined. We don't measure them all. We take a sample, we'll call that sample 1. We might then calculate a statistic, an average test score, average nutritional success, whatever measure we want. Now, hypothetically, or in fact in real life, we could do the same thing. We could take yet another sample. And these samples might be done by replacing the first group, put them back in the bucket, if you will, and take another sample, or first bucket out, then a second bucket of remaining children. All kinds of ways to do this, but we can imagine taking 2 samples from the source or target population. And you can do that again. Now we have 3 samples. And again, 4 samples. And from each of these samples, we can calculate a statistic: average health, average BMI, average nutritional success, whatever measure we like. Each of these statistics from their respective samples has neat properties. What happens is, interestingly, when we put these sample statistics measured many, many times in a graph, we end up with what? The lovely bell-shaped curve. Here, we talk about this as the sampling distribution of the means or the averages. That's all it is. It's very akin to that quincunx machine I spoke of a few moments ago. Here, what's important to recognize is I'm graphing not the actual students' say BMI, but the average BMI from each sample. And I put it onto a graph, and then it makes this bell-shaped curve. It's a pretty fascinating idea, and that's what drives how we understand so much of our statistical inference. By which I mean we have a sample calculation, and we're trying to infer what the population parameter is. And so we want to know how close we are and how much we might be off and how many times if we did this study over and over again. It's that idea that drives this fascinating thing called p-values. For some of you researchers, you'll know this idea well. For some of you who haven't been steeped in this, that's okay. The key idea I want to suggest to you is that lots of research that you'll read, if not see in the news or talk about, will be based on this idea of a p-value. And so I want to spend a few moments talking about what that is and what that isn't, so that you become better consumers of research and that you use p-values, if you endeavor to do so, perhaps more properly. So here's the story of p-values. Imagine you collected some data and estimated an effect. So you did an intervention on a school and you said, okay, it has this impact on child well-being, measured by a 1 to 10 scale or something. And so, okay, the students in the group that got, say, meditation in the school, mindfulness training, have a better sense of well-being than the kids who did not. Great. So maybe the difference between those who were treated with the mindfulness and those who were not is 4 units. The question is that difference of 4 between treatment and control, is that true in the parameter space, or does it have to do with the idiosyncrasies of this particular sample? Because in science, what we want is to have that truth in the parameter or total population space. That's the objective. And so we want to know whether the natural variability of doing that study over and over again in the same set of schools, hypothetically, would yield the same measure, 4. Or would it sometimes be 2, or maybe -20? How big is that spread? How much variability is there? Well, to be simple, we can assess this with some statistics by having the difference, 4, divided by the standard error of 4, the standard error of that change or the delta. The standard error can be a complicated calculation. I don't want to get into it here, but all this really is some difference we measure, 4, divided by an estimate of the variability we might expect had we done the experiment over and over again. And we call the ratio of these two values, the difference divided by the standard error, t for t statistic. Another more perhaps intuitive way to understand this is in the top part, the numerator, we call that the signal. In the bottom part is the noise. And so we want to understand of can we hear the signal given the noise. So if there's lots of noise, it's harder to hear a smaller signal. And so if I'm whispering in a quiet room, can you hear me? Probably yes. But if I'm whispering in a loud, crazy room or an airplane or a rock concert, you can't hear my whisper. And so what we want to do in our research is to design it with as little noise as possible so we can hear those small, sometimes whispering effects of our interventions more clearly. Alternatively, we want to have a bigger impact. So we're changing health so dramatically, reducing health disparities so dramatically that even in a stadium where there's lots of noise, we can still hear that effect. And so that's all that statistical analysis is really doing, trying to disentangle that signal from the noise. So there's two things we can do in our research: have a bigger impact and or have less noise. The rest is kind of details. Now these two things, the numerator and the denominator, the delta and the standard error, form a number, of course, and that number is, in this case, the t. And then we can sometimes assess that on a standardized scale to see, hey, is this due to chance alone? Or is this difference real? Is it bigger than zero? And that's what that p-value thing is all about. So I'm going to read a little bit from this slide. Typically, we calculate a p-value associated with a statistical test. Then we see if the calculated p-value is less than some threshold, typically 0.05, which means 5% error. So 5% of the time we can accept the error, 95% of the time we get it right. If it is, that is, if it's less than 5%, we can reject what we call the null hypothesis of no effect. This is some funny language, but we say we reject the hypothesis of no effect, which of course implies there is an effect. Our intervention worked, and we can discern it statistically. And so we claim, if that happens, that our effect is statistically significant. And this seems to mean that the estimated effect is probably not due to chance alone. Does it mean always? No, it means probably, because in science we're typically provisional. So what does this really mean? Well, we can make another diagram for some help here, and you can see this bell-shaped curve, I hope, on this sort of purplish blue background, and the bell-shaped curve has a yellow line. In the tails, on the outside of the bell-shaped curve, you see I've highlighted some areas, and those are in orange-reddish. Those represent together 5% of the whole bell-shaped curve. In the middle, which is still that purplish blue, is 95%. So that each tail has 2.5%, or 5% of the total. Well, all a p-value is saying that my effect, whatever it is so far out in one or the other tail, big or small, that we can reject the null of no effect at all. And that's what's happening here with all this p-value stuff. Now you probably want to read a little more about this, but that's all it is. It's sort of that simple, which is the point I'm trying to get across this afternoon. So technically, p-values are a mixture from some deep philosophy from friends we learned earlier in this course, Fisher and Neyman and Pearson. This is now Egon Pearson, old Carl Pearson's son. But there's lots of confusion and ignorance, and many people make interpretive errors. Increasingly, researchers are saying we should be more and more careful with using p-values, and some of us are saying we should have a different approach, what we might call a Bayesian approach. Some of that doesn't matter. The key idea is be cautious with using or reading to evaluate studies with p-values. Here's just a simple explanation for your own use. A p-value, if you read it or calculate it, of 0.04 tells us that if the null were true, that is, if there's actually no effect of the intervention, an effect of at least as large as we measured, 4, 20, 70, would occur 4 out of 100 times, or 4%, which is to say we have this level of error of 5%, but we have 4% times out of 100 that we'd have this crazy thing due to chance. Everything else is due to some real effect. So a p-value could be said to represent the strength of evidence against no effect. It gets a little technical. What we'd like to say is the p-value is some measure of the probability of success. But it turns out we can't do that for some logical reasons, which is yet another reason we should be cautious when reading or using p-values. Here's sort of a little slide that always makes me chuckle. You might be able to see that on this little cartoon that's all over the web. There's a chimpanzee-looking creature on my left side, and this is someone sort of pre-training in statistics, Homo a priorius. And then this person grows into an early human being, perhaps, and this is Homo pragmaticus. And then they grow and develop and evolve a little further, and they become Homo frequentist. And then they grow further and evolve further still, become Homo sapiens, that us. And then when they evolve yet further and figure it all out, they become Homo Bayesians. And for you statistically minded people, this is sort of a chuckle. It's a bit of a joke saying, as we evolve, we all become Bayesians. And the reason that is because we'd like to talk about the probability of our hypotheses. The probability that this hypothesis of this intervention changing that amount of health is true or not. We can't do that with our typical methods. It just doesn't work logically. But if you want, you can think that way casually to have a richer understanding of what this is all about. Now, almost finally here, I want to just close by saying for over 50 years, every major statistical methodologist that I've ever read urges caution with p-values and its cousin significance testing. Statistical significance and p-value say nothing about the importance of a study. So if you're reading some work and it has a big or small p-value, that doesn't mean it's important or not. It just means that it has some statistical properties of this or that amount. So I would like you to separate the importance of the research from the statistical properties of the analysis. They're related, but they're not one and the same. And finally, as you can see in the last bullet, you can't compare p-values across studies or even across variables. So p-values don't reflect the strength of relationships. They're sort of study-specific. Again, all of this is to say is as you get more sophisticated, if you're not already, be a little cautious of this p-value approach to understanding our work collectively.